In this video, we are going to learn what we call the Bernoulli rule. Sometimes we also call this rule the L'Hopital's rule. So Bernoulli is the one who came up with the idea, so we call this the Bernoulli rule. So let's look at this limit problem. So limit when x goes to 1, ln x divided by x minus 1. So if you look at the graph of the log function, so this is the graph of the log function. So asymptote and it goes to infinity, and at 1 it is 0. So this is the graph of the ln function, natural log function. So that means what happened when x goes to 1, the top goes to 0, bottom is also goes to 0. So this is a 0 over 0 situation, and we know that in mathematics 0 over 0 doesn't have a meaning, so we call these are indeterminate forms. Because why we call this indeterminate, the value is not exact, so we don't know what's the value of this one. So if you have a situation like that, so what can happen is it can be 0, it can be infinity, or it can even be some other finite values. It can be anything. So so the idea of this video is to learn how to find the limits of things like this. So we use this Bernoulli rule or the L'Hopital's rule to find limits of indeterminate forms. So what we can do, we can break this into 4 different types. So the first type is this. So it's type 1. So type 1 is what we have is 0 over 0 or infinity over infinity. So it can be positive or negative infinity, so we don't worry about the types. It's one of the infinities. That's a type 1. And then we have type 2. So we have type 2. So what is type 2 is sometimes what happens, it is 0 times infinity. So when you have product like that, 0 times infinity, again anything can happen in this case. It can be 0, it can be infinity, or it can be some other finite values in between. That's like type 2. And then we have type 3. Type 3 is like things like that. So you can have like infinity minus infinity. So when you subtract two large infinities, so we cannot exactly say what's the value is. It can be infinity, it can be negative infinity, it can be a finite value also. And then the last type is this one. So it's a type 4. So type 4 is like things like this. So it can be 1 to infinity. Because it's not really 1, it's a limit 1. If it is 1 to infinity is infinity, but that's not the case. What will happen is it's not 1 exactly, it's like going to 1, it's a limit. So that's one case. And then 0 to the power 0, that's also we don't know. And then also infinity to the 0 power. So those ones we don't know. So that's the all three in one type. So there are 4 different types. So let's try to learn one by one. So let's go to type 1. So type 1 is this a type 1 indeterminate form. That means 0 over 0 or infinity or infinity. That's like a most common one. And when you have any other types, what we try to do, we try to bring it to one of those forms. So so let's try to look at the result. So what we call the Bernoulli rule or the L'Hopital's rule. So what it says, suppose f and g are differentiable functions. You have two different functions that you can differentiate because you try to take the derivative. So it makes that you can take the derivative, differentiable functions, and g prime x not equal to 0. So that is what is in the denominator. So you make sure that that's not equal to 0. Near a. So we don't worry about what will happen at a. Near a should be differentiable and shouldn't be equal to 0. Near a. Now if one of these happen, so if the limit when x goes to a, fx over gx equal 0 over 0. That's the first case, 0 over 0. I mean the ratio becomes 0 over 0. Or infinity over infinity. That's the second one. Infinity over infinity. So it can be one of those infinities. If this is the case, if 0 over 0 or infinity infinity, then we have this interesting result. So what happened is then the limit when x goes to a, fx over gx is equals to the limit of the ratio of the derivatives. So what we do, we take the derivatives of separately. This is not the quotient rule. This is not the quotient rule. It's very, very careful. This is not the quotient rule. What we do, we just take the simple derivative of the top, take the derivative of the bottom, and then we divide the two and then take the limit. So this is, so that limit, original limit is equal to the limit of the derivatives if the limit on the right hand side exists. So what will happen, sometimes the right hand side may not exist, so then they are not equal. So if they are equal, no, if the right hand side exists, then they are equal. So that is the main result, then this is what we normally call the Bernoulli rule or the L'Hopital's rule. Okay, so it's like a very interesting result. So now let's look at some special cases that we need to remember. We can make the following remarks about this result. The first one is, this is not the quotient rule. The quotient rule is completely different from what we have. Here what we do is we take the derivative of the function separately and then divide. So this is not similar to the quotient rule. Number two, if f and g are continuous, we're going to consider the look at the condition differently. What we do is we just simply said check whether f, a and g are 0, not the limit, instead of the limit. So if the functions are continuous, we can just do that. And number three, so this is also works for one-sided limits. So if you have one-sided limits, still you can apply the same rule. The last one, a can be finite or infinite. So a can be finite or infinite. Okay, let's look at the first example. As the first example, we have find the limit when x goes to 1, ln x over x minus 1. So that was the problem that we get stuck. So let's see how we can do this now. So you can see that, so I'm going to repeat the question first. So as we see earlier, so you can see that when x goes to 1, you can see the top goes to 0 and the bottom also goes to 0. So we write it like that because this is the condition that we check. So we see that it is a 0 over 0 situation. So we write it like that. That means we check the condition. So what we do according to the result, what we want to do is we want to find the derivatives of the two functions, and we know that the derivative of a natural log function, so derivative of a natural log function, this is something that we need to remember, is equals to 1 over x. So that's the derivative of a natural log function. So that means, so we write limit x goes to 1, derivative of the top is simply 1 over x, the bottom is simply 1. Now we can simplify this one, so we can write this one as limit x goes to 1 over x. And then what we do, we check whether this limit exists. If this limit exists, then they are equal. So, and when x goes to 1, this goes to 1. So that means the original limit that we are looking to find is 1. So it's a very simple approach. You can see whether you can do this like using other techniques. So it will be a little difficult because we don't know how to factor log yet. So in Calc 2, you're going to learn a Maclaurin series for these ones, or in this case a Taylor series around 1. So you can do that, and then you can think of like another way to get the answer. But right now this is the like easiest way to do this. Okay, let's look at another problem. As the next one, we have this interesting limit problem. This is one of the celebrated limit in calculus. So when x goes to 0, sin x over x, we know this result. This is something that we prove using geometry. We know the answer is 1. So, but now we're going to give you a different answer, different proof for that, why this is 1. And then clearly you know that when x goes to 0, because of the graph of the sine function, and we know the graph of the sine function is like this. It's going to pass through 0 and then go up, down. So like that's a sine. And then it's clearly, we know that when x goes to 0, it is 0. So that means it's again a 0 over 0 situation. So we can write, so we can use L'Hopital's rule to solve this problem again. So we can start like this. So we have limit x goes 0 sin x of x, and then again we check the condition. So you can see that when you check the condition, the top is 0, bottom is 0. So you always need to write it, then you check the condition. And then what we do, we're going to replace these original functions by their derivatives. So derivative of sine is cosine, that we know, and derivative of x is 1. So now what we can do, we check whether this limit exists, and you can see if you look at the cosine graph, so the cosine graph, and what will happen in the cosine graph, you can see start at 1 and then go down and go like that. That's the cosine graph. This is the cosine x, and you can see at 0 it is 1. So it is 1, so that means it is So it's a cosine 0 over 1, so which is 1 over 1, which is 1. So you get the answer 1. So this is how you prove that the limit of sine x of x equal 1 using non-geometric argument. Okay, so let's look at one more problem before we go to the next type. And you can see more problems in the practice problem set. So there are several different problems solved in the practice problem section. So, but this is just a theory one. So let's look at one more example before we move to the second type. How about this? So we have limit x goes to 0, square root 1 plus x minus 1 divided by x. And we know how to solve a problem like this one. So normally we solve these kind of problems using the conjugate, multiply by conjugate arguments. You can multiply by the conjugate of the top and the bottom. So that's like a normally the algebraic technique to do it. But let's see how we can use the L'Hopital's rule for this problem. And you can clearly see that when x goes to 0, the top goes to 0 and the bottom also goes to 0. So it's again a 0 over 0 problem. So what we do, we take the derivative. So it's a limit when x goes to 0. So we take the derivative at the top. So it is the chain rule. So you can see the half power. So that means it's going to be 1 half 1 plus x, subtract 1 negative 1 half times 1, we don't write it, divided by 1. So if you rewrite it properly, taking the bring in the positive exponent, so you can write this one as 1 over 2 1 plus x square root. Now what we're going to do is we're going to send x to 0. When send x to 0, you can see that you're going to get 1 half and the limit exists. So that means this should be the original limit. You can try the following problem as an exercise. This is part of the practice problem set. Find the limit when x goes to 0, x minus sine x divided by x cube. So now let's try to look at a infinity problem. So let's do an infinity of infinity problem. So let's say find limit when x goes to infinity, ln x divided by square root x. So again, if you look at the graph of the natural log, and you clearly know that when x goes to infinity, the function goes to infinity. So when x goes to infinity, you can see the y value goes to infinity. So this is clearly infinity of infinity problem. So that means we can use the Bernoulli rule or the L'Hopital's rule as before. So let's write. So you can see this is infinity when x goes to infinity, and then also bottom also going to infinity. So it's infinity of infinity problem. So what we're going to do, we're going to take the derivative of the top and the bottom. So ln x, we know the derivative of ln x is 1 over x, and the bottom is a square root function, so 1 half power, so it's a 1 half x to the negative 1 half. So now what we're going to do is we need to use algebra to simplify this one. So the best way to simplify this one is try to get the denominator 1. To get the denominator 1, what we can do is we can multiply the top and bottom by 2 times x to the positive 1 half. So multiply by 2 times x to the positive 1 half. So when you do that, you can see the bottom functions get cancelled out. So these two get cancelled out, and then you're going to get 2 times 2 over, you can see x and square root x 1 half get cancelled, so you get square root x, so 2 over square root x, that's what you get. And then you can clearly see that when x goes to infinity, so since x is in the denominator, and we know that any functions, we know this result, so what the result is limit when x goes to infinity 1 over x to the any power. If it's the denominator, this is 0. So we assume that p is positive. So any power, so this is 0. So because of that, you can see the bottom function goes to 0. So this limit is 0. So let's do one more infinity problem. So we have limit x goes to infinity, ex divided by x squared. And clearly you can see, we know the graph of the exponential function. So the graph of the exponential function looks like this. It's passed through 1 and grow exponentially. That's why I call exponential. And then you can see in this case also, when x goes to infinity, the top goes to infinity and the bottom goes to infinity. So it's infinity over infinity problem. So what we can do, we can replace the original function by their derivatives. Derivative of ex is ex, and the derivative of the bottom 2x x squared is 2x. And then what will happen is, you can see this is again infinity over infinity. So that means we can use the rule again. So we take the derivative again. So we can write this one as ex now divided by 2, and then that's like a constant, and then so that means this just follow the behavior of the exponential function, and when x goes to infinity, ex goes to infinity. So the answer is infinity. So these are some of the type 1 problems. So let's try to move on to type 2 now. So as type 2, we have indeterminate form 0 times infinity. So we have 0 times infinity. So in this case also, like it's not clear what's going to happen, because one is going to 0, one is going to infinity. So we don't know which one is going to win. So if you get something like that, so we have several steps. So what we're going to do first, we're going to bring this into either 0 over 0 or infinity over infinity form. So bring this to, so bring this to either 0 over 0 or infinity over infinity. We do the easy one, so it doesn't really matter. We do the easy one. Sometimes it's easy to bring it to 0 over 0, sometimes it's easy to bring it to infinity over infinity. Okay, and then after we bring it to that, then it's a type 1. So that means use type 1 after that. Use type 1 method. Okay, so let's look at a problem. So let's say limit when x goes to 0, x times ln x. So if we have this problem, actually this problem doesn't have a meaning, because when x goes to 0, ln x, the limit doesn't exist, because a log is not defined for negative values. So that means what we can do, we can make, say, 0 plus. So now this is all right. So this is a good problem. Okay, so now we can see that when x goes to 0, again, if you look at the graph of the natural log function, so this is the graph of the natural log function, and you can see that when x reach 0 through larger values, through positive values, and you can see that this goes to negative infinity on this side. So that means this is a 0 times infinity problem. In this case, negative infinity, but it's an infinity problem. So in 0 times infinity problem, you can just take the derivative. So what we're going to do first is, we're going to write this one using the 0 0 form. So what we can do, we pick the easy one. Easy one here is x. So we can divide the top and bottom by x. That means bring x down. So we can write this one as limit x goes to 0 plus, we leave ln x there. What we do, we divide the top and bottom by x. So that means this will happen when you divide the top and bottom by x. So you get ln x divided by 1 over x. Now what we see, that you can see when you do that, this problem is when x goes to 0, we know that ln x goes to infinity, that's we already know, and all negative infinity, but we can say infinity. And when x goes to 0, 1 over x goes to infinity. So it's an infinity problem. So that means we can use the derivatives now. So we use the type 1 now. So derivative of ln x is 1 over x. And then derivative of 1 over x, how to do that? So you can write 1 over x like this, x to the negative 1, and then use the power rule. So if you use the power rule now, is negative x negative 2. That's what you get. And then what we can do is, you can multiply the top and bottom by x, and you can leave the negatives on outside because that's a constant. and then what we can do is we can multiply the top and bottom by x squared. When you do that, so what we do, we multiply the top and bottom by x squared. So we do that. So top get cancelled out, so you get 1. Negative sign we write outside, so actually bottom get cancelled out. The top becomes is 1 over x times x squared means x. So it just become x. So that means now when x goes to 0, x goes to 0, so it is simply 0. So the answer is 0 actually. So x times ln x, the limit is 0. So it's like a very useful result. You use this in when you do series problems. You can use this again. Okay, so this is how you do type 1 problems. But let's do one more type 1 problem, type 2 problem. So as the next one, we have limit x goes to infinity x times sine 1 of x. So clearly when x goes to infinity, this part goes to infinity. And then what will happen to the other one? So you can see when x goes to infinity, 1 of x goes to 0, and the sine, and we know that the sine 0 is 0. We know this result, sine 0 is 0. Since sine 0 is 0, you can see this part goes to 0. So it's infinite times 0 problem. So that means, so we can do it like that. So what we do is we can bring this to 0, 0, infinity over infinity. So you can see in this case it's easy to bring the x term down. So we can leave the sine 1 over x in the top and divide the top and bottom by x. So we can write this one as 1 over x. So that's the first step. Now when you do that, and you can see that now it is the top goes to 0, bottom also goes to 0 situation because x goes to infinity. So it's a 0 over 0. That means that we can take the derivatives now. So we can take the derivatives. X goes to infinity. So when you take the derivative, sine means cosine 1 over x, and then take the derivative of 1 over x that we took earlier. It is negative 1 over x squared. That's the derivative of 1 over x. Use the power rule. And the bottom again is the power rule. It's negative 1 over x squared. It's the same term. And then now what will happen is you can see that these two terms get cancelled out. So so you simply get the limit when x goes to infinity cosine 1 over x. So what will happen is when x goes to infinity, 1 over x goes to 0. So this term goes to 0. So that means this simply becomes cosine 0. Cosine 0 is 1 according to the cosine graph. Well, we know the cosine graph. Cosine graph is like this. So it's going to go like that and then go through 1 and go like that. That's a cosine graph, and you can see at 0 it is 1. Okay, so the answer is 1. And then you can also do this problem using a different technique, and I have put a link to the technique. So you can do this problem like in different ways also, like without using the L'Hopital's rule. You can probably say like h equal 1 over x, and then you can solve it. Okay, good. So let's go to the next type. So we have type 3, which is the indeterminate form, infinity minus infinity. So you can subtract infinity from infinity. So this we don't know. It's not 0. It can be 0, but it's not 0. We don't know exactly 0. So it can be 0, it can be infinity, it can be negative infinity, or it can be any other value as well. So if you get a problem like that, the basic tool is we use algebra to simplify first. So use algebra to simplify. So use algebra to simplify, and then we use one of those types. So use type 1 or 2 depending on the problem. So let's look at the problem and see how things gonna go. Let's say we have a limit x goes to 1 plus 1 over ln x minus 1 over x minus 1, and we know that ln 1 is 0. So that means so it's a 1 over 0 and going to 0. So that means it going to infinity. So this is infinity, and also the same thing, this is infinity. So it's infinity minus infinity problem. So when you get a problem like that, what we normally do is we use algebra first. So we just simplify. We just use the cross multiplication here, or what we call as going to 1 plus. So or what we call the 3a argument Remember 3 arguments, so we use the 3 arrows. So we have this arrow, that arrow, and then this arrow. So it's a 3a. So we can use a 3a argument here. So we're going to multiply these two first. So you're going to get x minus 1. And then we're going to multiply these two. So you're going to get ln x. So it's a minus ln x. And divided by the third arrow, that's the product. So it is x minus 1 ln x. And once you do that, and you can see now what will happen is when x goes to 1 plus, so you can see, so this term goes to 0, and then this term also goes to 0. So it's a 0, and the bottom is also 0. So it's become a 0 over 0 problem. So type 1. It's type 1. So that means we can take the derivative now. So let's take the derivative. So if you take the derivative, you're going to get x goes to 1 plus, derivative of this one is 1 minus 1 of x. And here you have to use the product rule. So let's use the product rule. So take the derivative of the first one times the second function, and then plus derivative of the second function times the first function. And then how to simplify something like that? So the easiest way to simplify this one is multiply the top and bottom by x. That's the easiest way to simplify this one. So if you multiply the top and bottom by x, you get limit x goes to 1 plus, become x minus 1, the top. The bottom become x ln x, and then here you get x minus 1. You can see now, we see what will happen now, and then when you take the when x goes to 1 plus, you can see it's again 0 over 0 problem. It's again 0 over 0. The reason is this term goes to 0, and this term goes to 0, and also that term goes to 0. So it's a 0 over 0. That means we take the derivative again. So when you take the derivative, the top become 1, and in the bottom you're going to get 1 times ln x. It may be a good idea to like get a paper and do it like with me, so then you can see it. And times 1 of x times x, and then plus 1. And then you can see you get cancel out x and x, 1 of x and x is become 1. So that means this is simply going to be limit x goes to 1 plus 1 over ln 2, not ln 2, ln x plus 2, ln x plus 2. That means when x goes to 1 plus, this term goes to 0. So that means the answer becomes simply 1/2. Very interesting. So you get 1/2 for this one. So you can try this problem as a practice problem. So the limit when x goes to 0, 1 over sine x minus 1 over x. Okay, so let's go to the next type, and you can see more problems in the practice problem set. So let's do let's go to the next type. So in this one, we have several different indeterminate forms. So one is we can have 1 to infinity, that's one type, 0 to the power 0, or infinity to the power 0. So those are the other types. They are all like same types, because we can use the same argument for these kind of problems. So for these kind of ones, what we can do is we can use the log limit argument. So we can use log limits, log limit problems, log limits. We already know how to do the log differentiation, like when you want to do complicated ones, or power for power function, then we use a log differentiation. But here what we use a log limits. So the approach is very simple, like same. So we can use this main result. So if the limit when x goes to a, ln fx equal L, then what will happen is the limit when x goes to a to the function is simply becomes e to the L. The reason is we know this result. We know that like when you write ln a equal b, this is if and only if. That means a is simply here you can see the base is e. So e to the b. So b is the power. B is the power. So we use this result. So when you have ln a equal b, that means a equal e to the b. So we use that same result. So that's exactly what we use here. So then mean from this one, then you can find the limit. So if we know the ln fx is L, the limit of ln fx is L, then limit of fx become e to the L, e to the L. So so that's the main result we use, and the method is this one. So we're gonna do is the first step is take. So we can or you can say let y equal whatever the function we're gonna take. We're gonna pick that part, the function part, and then what we do is take ln of both sides. Take the natural log of both sides, and then find the limit. So next step is find the limit. Find the limit. So let's look at a problem. Let's say we have this problem. Find the limit when x goes to 0 plus x to the 1 of x. So we want to make sure we put x to the plus, because otherwise, like, it might try to find roots of negative numbers. So that's why we want to make sure a 0 plus. But what happened here actually? You can see when x goes to 0 plus, so the base goes to 0 and the exponent goes to infinity. What do you think about that? When you have 0, you multiply 0 times infinite times, will this grow or will get smaller and smaller? You can see clearly this is going to be 0. So this is not the indeterminate form. So we know this one is 0. So, but what happens if you have this problem? Let's say we have x goes to infinity, x to the 1 of x. Now you can see things are different now. You can see the base goes to infinity, but the index goes to 0. That we don't know, because one grows large, one grows smaller. So in this case we don't know. So this is the indeterminate form. So this is the indeterminate one. So this is indeterminate. So that means we need to use the technique for this one. So what we're going to do, according to the argument, what we do, we're going to set let y equal x 1 of x. That's the first step. After we do that, then we take ln of both sides. So take ln of both sides. Once you do that, then you're going to get ln y equal ln x to the 1 of x, and you can see when you from one of the log properties, if you have power, the power going to come out. So you can write this one as 1 of x ln x. Now we can take the limit, and you can see when you take the limit now, so let's say limit when x goes to infinity, in this case ln y. So we take the original limit. So it's a limit when it goes to limit when x goes to infinity, you can write this one as ln x of x, and you can see when x goes to infinity, this is an infinity of infinity problem. Since this is infinity of infinity, we take the derivatives. So it's a limit x goes to infinity, take the derivative. So it's 1 of x over 1, and you can clearly see that when x goes to infinity, this can go into 0. So the limit is 0 because it's 1 of x over 1. So the limit is 0. If the limit is 0, now what we can do, we can write using the exponents now. We can write it like this. So we have limit x goes to infinity, ln y equals 0. Now what we can do, we can rewrite this one using the log form, exponential form. So we have ln a equal b, which is equals to a equal eb. So it's the same argument here. That means if you bring the limit inside, so we can write this one as the limit when x goes to infinity, y means x to the 1 of x, equal e to the 0, which is 1. So the answer is 1. So 0 is that one. So the answer is 1. So it's very interesting. So we can do one more problem before we finish this discussion. Again, like really interesting problem. So let's look at this one. This is the last problem of this discussion. So let's say limit when x goes to infinity. So let's do 0, 1 plus x to the 1 of x. So it's like a very interesting problem. So what happened here? And you can see when x goes to 0, so this term goes to 1. I say 1 plus x goes to 1, and 1 of x goes to infinity. So 1 of infinity is another indeterminate form. So as before, what we're going to do is we're going to take this part as y. So so as before, so we're going to say y equal 1 plus x to the 1 of x, and take ln of both sides. So let's say ln y equal, once you take the natural log as before, 1 of x comes out. This become ln 1 plus x. Now when n goes to infinity, and you can see that, so it's a limit when x goes to infinity, y equal limit x goes to infinity ln 1 plus x over x, and you can see this is a infinity over infinity problem. So take the derivatives, x goes to infinity. So when you take the derivative of the top is just 1 over 1 plus x, that's the derivative. The bottom derivative is 1. So that means actually in this problem x goes to 0, not infinity. So we'll fix it. So it's a 0 over 0 problem. So it's a 0 over 0 problem. And then when x goes to 0, so you can see this goes to 1 because x goes to 0. So 1 over x, 1 plus x goes to 1. That means the final answer is e to the 1, which is equals to e. So the answer is e for this problem. So it's like, remember this one. This is a very interesting problem. So again, we discuss all 4 techniques of the L'Hopital's rule or the Bernoulli rule, and you can see more problems in the practice problem sets. So we have 2 different sets. The first one discuss easy ones, the second one discuss more difficult ones. So you can look, after you study this one, then you can look at them and you can understand what's going on there. So thank you for watching.